always known if it's so bad. How bad is it? Really bad.
So
Like-
I might be looking at that soon.
So I don't even know what topic you're talking about, but I often tell people that the reason that I'm not a physicist is I didn't have a good physics teacher. If I had a good physics teacher, who knows, I could have been a physicist. But I had a great chemistry teacher, so I'm a chemist. Which, by extrapolation, means you're all going to be chemists. So no, I mean, if you need to, look outside of the box. Outside the box, you understand. Just don't do it all the time.
Yeah.
People will know.
And the good for your
Always
major class, like
explain
if
away
you wanted
something.
to and stuff like that, it will look bad. Like, you just do it for physics, it's fine.
That's why I'm like,
I'm good.
I might be able to.
Okay, so, blackboard. Blackboard, lab people.
Yeah.
You have 2 quizzes to take before lab starts. Lab starts at 8 a.m. Thank you for that. Tomorrow. Make sure that you take the pre-lab quizzes. When should we take a pre-lab quiz?
Pre-lab.
Before the lab. Make sure they get done. They're gonna be just, what?
There was 7 questions that I
Yes.
remember, and upon getting all of them right, it gave me a 7 out of 10.
That is what happened to me too.
Yeah.
Blackboard's like that.
Okay.
Big
So-
blackboard.
The lab safety quiz doesn't work.
I know.
Even though it's okay, it's really weird.
I know, because I just don't.
Oh, okay.
Yeah,
Nice.
Oh, so it doesn't.
yeah. Hey, listen, it's not gonna take you 50 seconds to take the lab quiz. There's a safety quiz, and there's the paperwork that you have to fill out every time you come to lab that we've always done on paper. And we're still gonna do on paper, but we're going to just make it like, I have read this, I understand these responsibilities, and check the box. Okay. Bless you. What else? Oh, little weekly mechanism quizzes. So the university has given me a fabulous laptop computer that will write with the stylus and everything, but it completely locks me out of uploading any kind of software to it. So I cannot use the structure drawing tool that I have elsewhere. So either I wrestle with the help desk for a while to get that, or I hand draw some structures, take photographs of them, and then you tell me what's wrong, which is probably how this quiz is going to go. But there will be weekly little quizzes about, look at this, tell me what you see, and that's it. Just look, recognize, move on. I
Regardless.
expect those to appear today, tomorrow. All right, so we know mechanisms. We've seen eliminations, additions, electrophilic, and we've seen substitutions, nuclear. Let's look a little bit more, but we're still looking back because we did this in chemistry, in organic chemistry 1. But it was the day that the camera glitched and missed the last 15 minutes of the lecture, so it's worth going over again. It was the part about 1-2 versus 1-4 electrophilic additions. At some point last term, we learned that there are 3 flavors of diene. What are those 3 flavors?
Conjugated.
Gonna let that one be last.
Isolated.
How could you recognize that you have an isolated diene?
The double bonds are right next to each other.
So this molecule would be an example of an isolated diene. It has an ene, and it has another ene, and there is 1, 2 single bonds, excuse me, between the pi systems, the double bonds. Name for that thing?
One, four, pentadiene.
How about this? That is also isolated. Each of those double bonds behaves independently. And because both of the molecules on the page currently are symmetrical, there's no Zaitsev's rule, the Markov-Post rule saying, yeah, go react that one first. Both identical. All right, what's the name of this one?
1,4 hexadiene. Or cycle, yeah.
They are isolated. Okay. Accumulated. How do you know when you see accumulated diene?
There's no single bonds between the pi systems.
There are 0 single bonds. Separating those pi systems. So a accumulated let's write them in. Properly. Like that. 1, 2, 3, 4, 5. Again, symmetrical. The deal with adding complexity to our molecules is we don't want to add so much complexity all at once. It's going to make things difficult to deal with. So when I introduce a second functional group to you, sometimes the molecule is going to be symmetrical, and then when we've dealt with it, we'll move from there. 1, 2, 3, 4, 5, with the double bond at the 2 and 3. So this is 2, 3 pentadiene. And if you called up the chemical manufacturer and asked them for some 2, 3 pentadiene, they would say, which one? You would say that way. I was going to say cis or trans, but yeah, we really, you know, is there an E or a Z isomer here? This is a bigger question. Not entirely certain that there is. Because to be E or Z across that double bond, these two groups, one of them has to be high or low. And it isn't at that carbon, it's at this carbon. So this is kind of cis-oid, and the other one would be trans-oid, but they're not strictly E or Z or cis or trans. They're somewhere in the middle because there's this mark line. Plus, when you call the mechanical manufacturer up and say, I would like to buy some 2,3-pentadiene, please, the response is probably, don't be stupid. That doesn't exist. Because jamming two double bonds next to each other makes these almost unbearably high in energy. And high energy molecules equals unstable. Not going to pretend that they don't exist, because you can make them, you'd make them in situ. If I needed this, I would set my reaction up and I would make it and I would use it on the spot immediately. But I'm not fooling myself that I could put it in a bottle, put that bottle on a shelf, and then advertise in a paper catalog and wait a year for somebody to buy that bottle. That would just be fooling yourself. All right, and then that leaves conjugated. How would you recognize a conjugated diene?
One single bond.
There is one single bond. Between the pi systems. Here's a pi system. And there are two bonds, if you count, between those pi systems going that way, but there is one bond, if you count, going this way. Double bond, single bond, double bond. When we go double bond, single bond, double bond, something special happens. Name of that. This one's a challenge. It's a challenge in a way that you might not think. All right, I'll entertain what it is to say. 3,3-dimethyl. 1, 4.
Oh, you're right. It is
Oh, you're right.
Yeah.
Yeah.
It's 5, 5.
Oh, you're
Good, Dan.
What was one of the very first things we told you to do?
Start.
Make the numbers that you use for your substituents as low as you possibly can. There are only 5 carbons in this molecule, and yet you've decided to put 10 numbers worth of naming into this molecule by making both of the methyls be at the 5. And then what? The double bonds need to be at the lowest possible number. Okay, so there would be two schools of thought right here. Let's work them through. 5 and 5 and 1 and 3 adds up to 14. And that's by going 1, 2, 3, 4, 5. If I made the methyls be at 1, then I could go 1, 1, 2, 3. And if you told me 1, 1, 2, 3, I would be able to figure out what that is. And if you told me 5, 5, 1, 3, oh, wait. 1, 2, 3, 4. Okay. That could possibly be right. 1, 1, 2, 4, that is 1, 2, 3, 4, 6. But that's a lower numbered system. And it wouldn't surprise me if people use that numbering system, but that's not the correct way. The correct way is to put the double bond at the lowest numbered system that you possibly can. So this is kind of a second, hey, welcome to Organic 2. This is a second level kind of a question, whereas doing the thing that the book tells me to do gives me a name that's completely rational. And if you wrote that down, people would be able to decipher it. But this top one is the correct answer, and here's why. What other arrangement of cyclopentadiene is there other than 1, 3? Here's a 5-carbon framework. Go put an isolated diene in it. Go try. Can't do it. Cannot do it. To put an isolated diene, they have to be 2 bonds away from each other. So here's the first one. And they're going to go 1 bond, 2 bonds. There's my other, it's conjugated. Okay, all right. Let's do, so I can't have an isolated diene. I can only have a conjugate. When I try to make an isolated diene, I make a conjugated diene. And then my other option is to make the cumulated diene, which doesn't exist. So when I say cyclopentadiene, it doesn't exist because it's too high mention. When I say cyclopentadiene, now I don't need the numbers. Cyclopentadiene is this. Okay, so if I say 1, 1, you're going to put 2 groups here. That carbon now has 5 carbons, can't possibly be right. That has to be 5. 1, 2, 3, 4. Has to be. So we don't even need the 1, 3. Put it in, because redundancy, being redundant, being pedantic is fine. It makes people not make any assumptions. Not technically needed. All right, now, isolated dienes exist. We can do 2 different electrophilic additions to them. And if I had methyls on one of those double bonds and hydrogens on the other, then one of them is going to be more friendly and attractive to an electrophilic addition than the other. Yeah? Because one of them is going to make a much better carbocation than the other one. So when they go asymmetric, now you start making choices about, which side of the molecule are we going to work on? But that's not as interesting as what happens here. When there is a single bond between the pi systems, what we get is something called resonance stabilization. And resonance stabilization lowers the energy of the entire molecule. All right, let's draw some Lewis structures and resonate some electrons and go through the rules again. Because these rules are important. It's going to lead us out of dienes being conjugated into trienes being conjugated, and the next step up being aromatic, which is a fabulous type of resonance stabilization, which is going to lead to a lot of stubborn behavior by these molecules. When a molecule is stable, it tends to do things in a way to retain that stability. And so when you make your products really super stable, they tend to not be good reactants for the next thing that comes. And when they do react and you force their hand to, they're going to opt out of some of the things that you've learned of being obvious. It's going to open up the second half of the textbook to us. Everything in the second half of the textbook has resonance in it. Do I need to go through Lewis structures? I need one of you to say yes. And then we'll do it. Because I don't want, what I don't want is week 15 of Organic 2 when it becoming clear that you can't draw simple structures. All right. Lewis structures describe covalent bonding. What is a covalent bond? How many? Between how many? To create a covalent bond, you share 2 electrons between 2 atoms. What atoms? Where will I find these atoms?
2 nonmetals.
Non-metals. Covalent bonding is not between metals and non-metals or metals and metals. It is between non-metals and non-metals. All right. number of bonds that an atom makes is a direct result of its valency, and that means, just look at the periodic table. So, group 1, group 2, group 3, group 4, group 5, group 6, group 7, and group 8. And if I'm in group 1, like a hydrogen, I make 1 bond. How many covalent bonds? Group 2. How many covalent bonds does magnesium make?
0.
It's a metal. It's not on our list. If I get to group 3, I've got aluminum. That's a metal. But above it is a boron. So boron's the only thing in group 3 that concerns me. There it is. I'm going to make 3 bonds. And I represent that as an H with a dot. The dot is the electron. And draw the electrons as far apart from each other as you possibly can go, because they repel each other. You get to carbon. Carbon makes 4 bonds, because it has 4 valence electrons. And to make a chemical bond, covalent bond, 2 electrons shared between 2 atoms. All right, that puts me at nitrogen. And nitrogen, we go 1, 2, 3, 4, 5. Because there are 8 spaces on the periodic table. 8 electrons, but those electrons inhabit orbitals. So the second period can be described by 8 electrons, but that's 4 electronic orbitals, 4 atomic orbitals. At some point we have to start pairing those up. This has 3 unpaired electrons. So this will give me 3 bonds, which is our next rule right here. Only unpaired electrons make bonds. That's not true, but it was true when we wrote it down in general chemistry. Get to 6. We look at oxygen. Oxygen is 1, 2, 3, 4, 5, 6. Has 6 electrons. 6 electrons, but it only makes 2 bonds, because 4 of those electrons are taken up in non-bonding pairs. These non-bonding pairs of electrons, or lone pairs, are not responsible for bonding between atoms. They are responsible for bonding between molecules, but not between atoms. And then group 7, I got a fluorine. And fluorine is 1, 2, 3, 4, 5, 6, 7, and therefore makes 1 bond. What about neon? How many covalent bonds is neon going to make?
0.
It's not part of the conversation. Okay? All right. We're going to combine the atoms together. Until every atom in the molecule has 8 electrons. With the big exception of H. Hydrogen is in the first period and cannot accept 8 electrons, doesn't have space. It needs 2. Hydrogen needs 2. If all atoms in the chemical formula have been used, but the valency still isn't 8, then we are going to make more bonds. Keep bonding until you make that valency be equal to 8. I'm going to scratch this. I'm not going to write that down. So in general chemistry, we write that if an atom appears only once in the chemical formula, it's probably at the center. That's not going to be true in organic, because I could give you fluorooctane. 8 carbons, what are we looking at? 17 hydrogens and 1 fluorine. Oh, that fluorine must be at the center. No, that's not how it works anymore. So there are 2 little additional rules there for general chemistry. If an atom appears one time in the chemical formula, it's probably at the center. If it appears multiple times, it's on the outside. And hydrogen is always on the outside because it only makes 1 bond, as is fluorine. Okay. Those are rules for constructing the molecule. Now, going to adapt those and add a little bit of detail. There are rules that describe what to do with the Lewis structures, if you have them, that are capable of resonating their electrons and delocalizing them. First of all, only the electrons responsible for pi bonds. Lone pairs. And lone pairs goes hand in hand with charges. Only those electrons can move. Rule 2 is a restatement of Rule 1. It's going to say the same thing, slightly different way. Sigma bonds don't break. Atoms don't move. So if I'm looking at a molecule, and that molecule can shuffle its electron density from one side of the molecule to the other, it's allowed to do that by rearranging its pi bonds and lone pairs and charges. It is not allowed to do that by detaching bonds, moving atoms to another place, and then reattaching them. That's chemistry. That's reactions. This is not. This is just something that the molecule does in flux. It just moves electrons from one place to another. All right, there is a hierarchy. The centers that you are going to move are only allowed to be separated by one single bond. So the areas of movable, not sure how you spell movable. Is there an E there or just the A? Okay.
No.
No.
There's an E.
Arm wrestle for it. Areas, yeah, there's no E there, is there? No. Sometimes you're very, very close to the board. Those of you that end up being teachers or bookmakers, you'll realize when you're very, very close to the board, sometimes you can't see. Areas of movable electrons must be separated by one single bond. Oh, here's another word. And then there is a hierarchy. I am going to move areas of high electron density to areas of low electron density. I'll say that again because I said it wrong. I'm going to move areas of high electron density towards areas of low electron density. Not to, towards. Negative charges move towards positive charges. How did that negative get there in the first place? Chances are it's a lone pair of electrons. Is going to move towards the positive, not to. Towards, in the direction of. Pi bonds will move towards positive charge. Negative charges will move towards a pi bond. So, you look at your molecule. If there is a positive and a negative in it, then the negative moves towards the positive. If there is a pi bond and a positive charge, then the pi moves towards the positive. It goes from the area of high electron density to the area of low electron density. But a negative trumps the pi bond, and the negative will move towards the pi. A pi on its own would not move towards the negative, but would move towards the positive. Get it? A lone pair will move towards a pi bond. a pi bond will move towards another pi bond. What would a positive move towards? What would a positive move towards? Nothing. That's a trick question. You're not supposed to fall for that. Negatives move towards positives. Positives don't move towards anything. Electrons flow from where they are and they go to places where they are not. The positive is validation that there are not electrons there. So you cannot have an arrow come away from a positive, not ever. Okay, let's do something. It might not be it might be immediately clear that that one is top of the list, a negative and a positive, because that's clearly negative, well, that's where the electrons are, and this is clearly positive, it's where the electrons are not. But it might not be immediately obvious why this pi to pi thing is dead last. When we do the pi to pi or lone pair to pi, we help by moving the electrons around, but we also introduce a complication that the molecule will punish us for. So you get something good, but then you get something bad as well. So let's look at the electrophilic addition to conjugated dienes. There is no better molecule to demonstrate this with than 1,3-butadiene. Small, is symmetrical, and conjugated. All right, let's do an electrophilic addition of your choice.
HCl.
When you react butadiene with HCl, you make the anticipated product. This one. What is the name of the product?
Retro.
I have 4 carbons. the double bond is more important than the substituent. That is 3-chloro-1-butene. And 3-chloro-1-butene is a named product in this reaction, but it is not the only product in this reaction. What else gets made?
1-chloro-2-butene.
1-chloro-2-butene is the other. Surprisingly, looks like this. Yeah, surprise. Okay, let's run through the top one because the top reaction is obvious. The second reaction reveals something that we should be expecting, but it's lurking there under the surface. Okay, so here's a reactant, there's a co-reactant. I'm going to need some curved arrows. Where does my first arrow start from?
Bond between the H and the Cl.
From here.
Oh.
Area of high electron density. This is a nucleophile. Where does it go to? Are we all okay with that bond being polar? Chlorine is electronegative. Hydrogen is on the left-hand side of the periodic table. Chlorine is on the right-hand side, which means this is a little bit positive, that's a little bit negative. Actually, it's pretty positive and pretty negative. Okay, so from the bond, from the middle of the bond, don't draw it from either of the carbons, from the bond. This is the pi electrons reaching out to grab it. Hydrogen can only make one bond. So if you're making a new bond to it, you have to get rid of the bond that already exists. Okay. That gives me one of these two carbons to put my blue hydrogen on. This one or that one? This one? That one? This one? Who says so? Markovnikov says because a secondary carbocation is better than a primary carbocation. If I put the blue hydrogen here, it leaves a positive charge on this terminal carbon. Don't do that. Don't put a positive on a primary carbon. Primary carbon's only bonded to one other carbon. It's not a good place for a carbocation. Secondary carbon bonded to two carbons. Good place. All right, and then off you go. That's your second step. So an electrophilic addition has an electrophile be the first step. Nucleophile be the second step. And Markovnikov says to do this part in the middle. All right, I've got 1 minute. Let's do it again. Same thing. The beginning of the reaction is going to be identical. Only now, going to allow the rules that I just clicked onto the board to kick in. It's going to add resonance. My hierarchy said I can move a pi bond not to the positive charge, towards the positive charge. That carbon only has 3 bonds and a positive charge. When I move the double bond, and look, new arrow, this arrow, double-sided. When I move the double bond to the middle, it's this carbon. Bad place for a carbocation. Bad place for a carbocation. But ends up getting it, and now the chloride comes and grabs that. But the fact that I've resonated the electrons between one place always stabilizes the molecule. The first reaction was quick, easy, made me a good product. That's kinetic. The second one goes through a horrible, horrible carbocation, but look what it's done to my product. My product is no longer the terminal alkene, it's now an internal alkene, better product. I had to go through an additional step to make it, but I ended up with the better thing. So I have a thermodynamic product and a kinetic product. The kinetic product is easy, you do that when it's cold. Thermodynamic reaction takes a bit longer. You need to warm that one up. Okay, so we saw this in OChem 1. This is going to pop up from time to time, but during a reaction we now have to be prepared for, oh wait a minute, I might be able to rearrange that and make something even better than I was expecting. Okay? I know, you're
Is it on?
no, it's not. It's only on paper. Come and get it. Depends.
Not late. You want something like that?
Yeah. Yep. We have a couple of experiments that we can do in lab where I can set you up in groups. You guys do it at a different temperature than them, and then we can look at what the product ratio is. And, oh, you got this one, and they got the other one.
You're about to keep it in that stack.
If you have the homework, make sure it gets to me today.